All right, so today in AP Physics, we're going to address, in this video anyway, one important question, which is, how do you determine the acceleration of something which is rolling down an incline, all right, as opposed to something that's sliding down an incline? Because they actually do not work the same way. Friction does not operate the same way on these two objects, okay? Even if I made them out of the exact same material, so the coefficient of friction is the same, the fact that this one is rolling and this one is sliding makes the accelerations be different, okay? All right, there's actually a couple ways you could come at like what the acceleration is. One would be figure out the final velocity when it gets to the bottom, and then go back and use kinematics to figure out what the acceleration is. That's not the one I want to look at right now, although we do need to talk about like energy for rolling things because it's different from the pendulum question that we looked at before. Instead, we're going to do this with the with forces. All right. So, what are some forces acting on this thing?
Gravity.
All right. We got some gravity. All right. What else we got?
Friction.
All right. And normal force. All right, now which way does friction go?
Up the incline.
All right, now it's actually a little bit weird with rolling objects, the direction that friction goes. In this case, that's the correct direction for friction. But when you're trying to determine the direction of a friction force for a rolling object, it's not just like, oh, well, it's opposite the direction of movement. In this case, it is. But that's coincidence. What you actually need to think about is the fact that friction is what produces the torque that makes the object rotate. So as this thing is moving down the incline, its rate of rotation is increasing like this. So that means the direction of friction must be up the incline in order to cause it to twist and rotate like that. All right, everybody okay with that idea? Okay, all right, so the friction force causes a torque that makes it rotate, all right? And it is increasing the rate of rotation, so that's why we put friction that way. Let's consider the other scenario where we have something that's rolling up an incline, meaning like somebody pushed it towards it, it's rolling along, and so it's moving this way, all right? Gravity and normal force are the same, stuff like that, okay? The direction of friction is not what you expect. If we had something sliding up an incline, I mean, if it's moving this way, then of course friction is in the opposite direction. Because, you know, for something like this, friction is opposing motion, right? Friction opposes motion or attempted motion. What kind of friction is this? Kinetic friction. What kind of friction acts on a rolling object? Static friction. So it doesn't have to operate the same way. Yeah?
So it's going up.
What? Yeah, it's kind of crazy because you look at that and you're like, but are you telling me the friction is helping it roll up the incline? Yes. That is actually what I am kind of telling you, yeah. It in fact does make it go further up the incline. The reason it's up the incline, though, has to do with the rate of change in its rotation. Okay, so as it rolls up the incline, is it going to be rolling faster or slower? Slower, right? So, and I'm not just talking about like how fast it's translating up the incline. We're not talking linear speed, which should be decreasing. We're talking about rotational speed. So its angular velocity should decrease as it moves up. So given that it's rotating like this, if friction continued to act down the incline, then we would have a totally bogus situation where it's rolling up the incline, spinning faster and faster, but also like slowing down, because that doesn't make any sense.
Physics.
Okay, so friction in this case acts up the incline because we need its rate of rotation to be less, right? It's rotating this way. In order for it to be rolling slower, meaning rotating slower, friction needs to act like that to produce a torque in the opposite direction. So the direction that we pick for friction is actually based on the direction of the net torque that must be acting on the rolling object. Okay, so any problems there? I saw a hand up, but it went down. Good, okay, all right. Okay, now let's go back to this picture so that we can actually do the calculations for it. We said it's static friction. That's actually like a pretty crucial fact in determining the acceleration as this thing moves along the incline. You're going to have to go with both forces and torque to work out what the acceleration is. Okay, so what are the x forces acting on this thing? All right. And what else we got? Friction, all right. And then equals ma. All right. Now, what we would do with a sliding object is probably then we would say, and friction is fun, and the normal force is mg cosine theta. So that means, and then you would plug in over there, and then it would be like exactly the same freaking thing. Okay, and rolling and sliding are not the same thing, right? They are different, okay? So that means we shouldn't approach the problem the same way. And the reason it's not the same is because the type of friction is different. This is what type? Kinetic. Kinetic friction is just fun. That's it. Okay, what's the formula for static friction? Less than or equal to. The friction is static here, so it doesn't equal fun. Unless you are like at the maximum angle that the incline can be before that rolling thing actually starts skidding. Right? I mean, if you put it at a steep enough angle, it will both rotate and slide, which is really messy. So we won't do something like that. Yeah, if it's slipping, okay? Meaning we won't mathematically work out any problems where it's rolling and sliding at the same time, because the math is just kind of gross for that. All right, but something like this where it rolls without slipping, we can do these. You just can't plug in mu mg cosine theta because that's not what it is. It's less than or equal to that, and odds are pretty good, unless this is a really steep incline, that it's going to be less than that. So instead of using this to get the friction force, we go to torque. All right, so what is the torque produced by friction? All right, what's the formula for torque?
Torque equals moment of inertia times acceleration.
Okay, all right, that's one of them, but how do you find a torque?
Force cross R.
All right, F cross R. All right, so, here's the radius of the object. So, just that. Why do I not need to worry about the cross part? Yeah, it's perpendicular, right? Yeah, radius, friction. So sine of 90 is 1. So we're good there. The torque would be just Fr. Okay. And that equals I alpha. All right. So at this point, I'm gonna, for you internet people, I'm gonna pause the video, and you're gonna pause too. All right. And then you're gonna make a couple of substitutions, just like the people in class are, and figure out what's supposed to happen next, so that I don't do all the thinking. All right. I'll get back to you in a minute. One brief moment. I didn't tell you what this was or what kind of an object it was. So let's say that it's a solid cylinder. All right, now you can do the question. All right, if you are tuning back in at this point, making a couple of substitutions. If it's a cylinder, then this is your moment of inertia, 1/2 mr squared. And if our goal is to solve for the acceleration of the thing rolling down the incline, then we need alpha to go away. And so we'll replace it with A over R, since A equals alpha R. Okay, next is we got to solve for the friction force, so we can plug it in up here, since we can't just say friction's fun, since we're not at the maximum angle. All right, so what did the friction force work out to from this equation? Bless you. All right, or 1/2 m², right? This cancels one of them. The other R cancels entirely. All right, so 1/2 ma. What do I do with that now?
Load it into your friction.
Okay. All right, so that means that equation is going to turn into mg sine theta minus 1/2 ma equals ma. Okay. And now we just got to group some like terms together. So we'll have 3/2 ma. The m was going to cancel, as usual. There we go. So 2/3 g sine theta. Cool. All right. Now, if we had a different type of solid, then this wouldn't be 1/2 here. It might be, for a sphere, you'd have like 2/5. And so then that would mean this wouldn't be 3/2, it would be 7/5. And so then we get 5/7 g sine theta instead. So the particular answer that you get depends on what type of solid it is. All right, but it doesn't at all, you'll notice, depend on the coefficient of friction or the mass, right? All those things cancel out. And the reason it doesn't depend on the coefficient of friction is because we're not at the maximum angle and it's not kinetic friction. The maximum angle where this is still going to be the acceleration is, however, determined by the coefficient of friction. So every now and then you might get a question where it says, and now it's at, what's the maximum acceleration that it could have before the thing starts sliding? At that point, you can say, all right, friction is fun. Now you can put in mu mg cosine theta and go from there.
And you wouldn't have to use the
Right. Yep. Okay. At least I think you wouldn't have to. Yeah, no, I don't think you'd have to. Okay. Any other questions with this? For your benefit or the people who might be watching later? Yeah.
So for a cylinder or something rolling just on a flat surface, I guess which way's the friction?
Okay, depends. So let's say that we had a cylinder, a wheel, okay, or something like that, right? So it's got an axle down the middle, and we pull this way. Okay. For something like this, I mean, if it's on a surface and we're pulling it that way, the force we're applying doesn't exert a torque at all because it's acting at the center of mass. So in this case, given that we know it ought to roll this way, the friction force would have to act in kind of the expected direction. There is, however, a question that you'll see in one of the homeworks. I think it's in this first set where where you have, instead of looking like this, it's like you've got a wheel and there's like a string wrapped around it, like through a groove or something, I don't know. And so the force is being applied up top, right? So they're like pulling on a rope that's tied to it. And in this case, the direction of friction is kind of unexpected. It works out that if